Okay, problem number 12 in the homework is a little more complicated. It asks you to calculate the magnetic field at this point P due to a very long wire that is bent into a quarter circle arc and then heads straight down. Before you try to do any calculations, part B of the problem asks for the direction of the magnetic field. So you can find that using one of our right-hand rules. You can remember that fields circle wires, thumb in the direction of current up there on the top. There's going to be a circular field that will be poking out underneath. So here at point P, this straight wire will have a field poking out. Or you could use that right-hand rule where we point our fingers of our right hand along the circular arc that's carrying current in the direction of the current. Your thumb gives you the field. So the field must be pointing out here at point P using either one of those right-hand rules. So at least we get the direction right. To get the magnetic field calculation, we're going to have to use the Biot-Savart Law, and it's kind of complicated. I will do that on the board. So I'm going to move the camera over, and I will set up the problem for you and let you finish it on your own time for the homework. Okay, so here's our really long wire that's curved into our semicircular arc. And you can break this problem up into three parts. Notice, again, I chose my origin up here, and I made the y-axis down positive just so we don't have to worry about negative signs. X-axis positive that way. And note, because the arc has a radius r, this point is a distance r over, and that's a part over. But there's really three parts to the problem. There's a very long straight wire here. We need to know the field here. There's a long wire here, and we need to know the field here. And then there's a quarter circular arc, and we need to know the field there. We need to add these three fields together. So can you use the long straight wire formula to find the magnetic field at this point due to this piece and that piece? Well, one way to find out is to do the calculation. So let's set up that calculation. So take a small piece of the wire. Since I'm on the x-axis, I'll call this dx, and it points in the direction of the current. That dx is a distance r to the point where you want to know the magnetic field. I'll call this big R now, to not be confused with our radius of our arc here. And the r hat vector would be here, pointing that way, so the angle theta is this angle. And remember, we're using the Biot-Savart Law here, which is mu naught I over 4 pi ds sine theta over r squared, where we're using a big R for that distance. So that's our Biot-Savart Law to find the field just due to that one little piece. Okay, well, if I want to know the field here, I need to figure out what sine theta is and what r squared is. First, I need to locate my piece of wire that I picked. I could say it's a distance x over from the origin. And then also notice there's a right triangle here. And so I could say r is this distance squared plus this distance squared square root. So this would be, this distance is little r, so we need to square that. And this distance is x minus r, because this distance is r. So this is x minus r here. All to the 1/2 power. That's just Pythagorean's theorem, where again, this distance here is x minus r, one side of the triangle. The other side is just r. Okay, sine of theta is the opposite over the hypotenuse. So sine of theta is little r over big R, where big R is given by that Pythagorean's type formula. So I can now substitute these in over here. So I got mu naught I over 4 pi. My ds is now dx. My sine of theta is little r over big R. And there's an r squared in the bottom. That means you have an r cubed on the bottom and a little r on the top. So little r comes up on the top. That's from the sine term. And you have an r cubed on the bottom. So I can write that as r squared plus x minus r quantity squared to the 3/2 power now, because we cubed something that was to the 1/2 power. Okay, so this is an equation for the field just due to this one little piece of current. If you want to know the equation for the field due to the entire wire that's straight up here, we have to integrate. So B would be integral dB, and we could pull all the constants out, mu naught I little r over 4 pi, and then you have an integral of dx over r squared plus x minus r squared to the 3/2 power. And now we just got to put our limits of integration in. Well, if you took a chunk of wire right here at the end of the straight piece, you'd be at x equals little r. And if you took a piece on the other end of that wire, it's out there at infinity. Okay, so this is an integral that can be done. You could use Wolfram Alpha or just remember how to do calculus, and you could solve this integral. Whether it equals the long straight wire formula, I'll let you figure that out. Okay, but you should realize that if you do the same kind of calculation for this long straight wire, finding its field at this point, you should get exactly the same formula. Again, use the same technique. Pick a dy, locate the piece, a distance y from the origin. It's going to give you exactly the same integral, but with y's in it. Okay, hopefully you can see that. Both are the same distance long, and they're the same distance from that point where we want to know the field. So they should have the same answer. So whatever you get for this first integral, if you double it, it'll give you the field of both straight pieces. Okay, then you can look in an earlier YouTube video where I did the magnetic field of a semicircular arc, and you could use that technique to find the field due to this quarter circle. Not surprisingly, you should get a field that is half as big as that previous YouTube video's answer. A quarter circle should have half the field of a semicircle. So once you've calculated the field of that quarter circle, and you've calculated the field using this integral, and you doubled it to factor in the other wire, you add all those numbers up, because all three pieces of wire have fields poking out here at that point. Add them all up and you get the net field. Have fun with this one. It's a tough one.